Mr. and Mrs. the Presidents, Honorable Presence, I welcome you. I have the great pleasure to present my work which concerns the development of an intelligent electronic sentinel for the monitoring and detection of meteorological phenomena due to global climate change. To do so, I organize my work into several sections. First section revolves around electronic sentinels. Second section focuses on design and architecture of an electronic sentinel. Third section is about the prototyping of our electronic sentinel. Fourth section deals with hardware and software design and implementation of our electronic sentinel. Fifth section is related to the meteorological phenomena targeted by our sentinel. Sixth section takes care of the simulation and its results. Finally, we close our work with a conclusion. In the last few years, the global warming of our planet occupies a preeminent place in the field of scientific research. To define with precision its present and future repercussions on human lives, for this purpose, a continuous and real-time monitoring of the physical quantities characterizing meteorological phenomena is necessary for their good understanding, as well as their early detection and the triggering of alarms during emergency situations. To this effect, our research work focuses on the development of an intelligent electronic sentinel. Our electronic sentinel will rely on artificial intelligence to enrich these knowledge bases and ensure the veracity of the phenomena it quantifies by avoiding triggering false alarms. The global climate change of our planet leads to the aggravation of several meteorological phenomena. To properly identify and manage these weather phenomena, it is essential to measure them over large geographical areas. One of the possible solutions to this problem is the use of new electronic entities for the detection and real-time monitoring of these weather phenomena. These entities must include different types of sensors in order to measure several physical quantities related to the triggering of these phenomena. These entities are called electronic sentinels. The main goal of the development of these electronic sentinels is to provide an optimal method of detecting meteorological phenomena and monitoring the environments in real time. Indeed, an electronic sentinel will be able to collect and process a periodic traffic of data from its direct environments of action, such as air quality, temperature, humidity, or from a remote environment through an extension of this same sentinel in the form of a collection of remote sensors such as soil moisture, the level of rainwater, the level of nitrogen in the soil, etc. On the other hand, the electronic sentinel carries out sporadic data processing in order to detect emergency situations such as forest fires, floods, or even alarming increase in air pollution. In addition, the electronic sentinels must be equipped with some form of intelligence to ensure the collection and processing of periodic and sporadic environmental data in order to report abnormal situations. To do so, we integrate new artificial intelligence algorithms. In order to better quantify certain meteorological phenomena, we collect environmental data from various physical environments. This involves the separation of our electronic sentinel into two distinct parts. The super sentinel, or the parent sentinel, ensures the processing of data collected by itself and its sub-sentinel, detection of emergency situations. Sub-sentinel, or the child sentinel, under the continuous control of the parent sentinel, it is considered as an extension of the latter. To ensure the correct functioning of our electronic sentinel, the latter should be composed of the following modules. The first module is the processing module. It contains a microprocessor coupled to a random access memory and a storage unit, a hard disk, in which a mini operating system is installed. It takes care of detecting emergency situations. To do so, the machine learning algorithm will be pre-installed on the storage unit to be assembled with our sentinels. A sensing module mainly made of local sensors integrated in the super sentinel and remote sensors in the sub sentinel. The third module is the transceiver module. This module handles in one hand the transfer of data and command packets between the sub and super sentinel, and on the other hand sends data and alarms to a remote server. The fourth module is the power supply module. We opted for the use of a solar panel linked to a battery and a voltage regulator. In order to put into practice all the elements we have discussed in the previous sections, we need to make a prototype of our electronic sentinel, super sentinel, and its extension sub sentinel. To do so, we will divide our work into several stages. The first stage is the specification of the required electronic components. The second one is the computer-aided hardware design. The third one is the hardware implementation of our electronic Sentinel, and the last one is the software design and implementation of our electronic Sentinel. In order to enable our electronic Sentinel to carry out its tasks correctly, we will use the electronic components listed in the following table when assembling it. This design allows us to virtually prototype our electronic Sentinel while reducing hardware and software costs. As a result of this step, we will have the electronic assembly diagrams for each components, and then we assemble them to have the final electronic diagram of our Sentinel in figure 8 and 9. Based on the final assembly diagram of our electronic Sentinel discussed in the previous step, as well as the technical characteristics of each electronic component, we proceed to the connection of the latter. For reasons of patenting of our prototype, we will show only parts of the assemblies, as shown in figures 10 and 11. The aim of our system is to detect forest fires or floods based on the data collected by the electronic super and sub-sentinels. Indeed, the collected data are periodically stored in the hard disk of the Sentinel and simultaneously sent to the remote server. After that, the data are used by our program, which is based on artificial intelligence, to indicate the presence of a phenomenon or not. In case of detection of one of the phenomena, the system sends the current data to the remote server, allowing a real-time monitoring. The core of our system is based on a machine learning algorithm known as the naive Bayes classifier. A naive Bayes classifier is an algorithm that allows to build a decision rule in order to predict the right classification from the labeled data. Its mechanism is divided into two phases, a training phase and a test phase, so that we can obtain a reliable model or decision rule that can decide if the current data indicates the presence of a phenomenon such as forest fire or flood, or if everything is fine. As I said before, the training is performed on labeled data. So what does labeled data mean? A labeled data or supervised data is data that has been labeled by an expert in the field. In our case, starting from a time series containing the values of the sensors used, a geographer assigns a label class, flood or forest fire or normal to each data according to the general cases. So the first phase is the training phase, which consists of using the labeled data to build up rules or a model that can provide a judgment close to the reality. As its name indicates, the Bayes classifier is based on Bayes' theorem. It shown in the equation 1. For application purposes, the equation is simplified based on the assumption that the data follow a normal distribution, resulting in equation 2. So we start the algorithm by calculating for each phenomenon A belonging to the labeled dataset, the average of A, the variance-covariance matrix of A, P to A, P to B to A, using formula 2, and put it in a vector. And then at the end we sort the vector and return the phenomenon P, having the largest P to B to A. The second phase is the test phase. It involves testing the model built from the rules elaborated in the previous phase to check whether the built model is reliable or not. In fact, the Bayes algorithm has already proven its results in the detection of anomalies, thanks to its great capacity of not being swayed by the noise, which is the main reason for which we have chosen it among the range of existing algorithms. Concerning the test results metrics, we have used two metrics to evaluate the results of our algorithm. The first one is accuracy, which represents the percentage of correct predictions compared to all predictions made, calculated using equation 3. The second metric is Cohen's kappa, as shown in the equation 4. So the reason why we've chosen this metric while we already have the accuracy is when we are confronted with a multi-label classification problem, sometimes the accuracy does not provide a complete picture of the model's performance. So in this case, we have to use this additional metric. So using these metrics, we have obtained an accuracy of 97.45% and a kappa of 91.88%, which shows that our algorithm performs pretty well, despite the fact that there are still a number of false positives and negatives, but it can be considered quite reliable. This research work in order to fully understand the functioning of our electronic sentinel, we focus on two almost opposite meteorological phenomena: forest fires and floods. Forest fires concern fires that spread in forest areas as a result of high temperatures. Detection of this phenomenon by the electronic sentinel is based on the following sensors. DHT22 informs us of a sudden rise in temperature and a drop in humidity. BMP 100 AC barometer detects a rapid decrease in barometric pressure. MQ2 detects smoke. MQ9 detects CO2. MQ 135 detects CO2. RCL5 PCS detects very low soil moisture. Our electronic sentinel is equipped with this GPS beacon. The exact position of the phenomenon's trigger will be sent directly to the civil protection. A flood is the submergence of an area by fresh or salt water. Detection of this type of phenomenon by our electronic sentinel is based on the following sensors: raindrops, which informs us about the presence of precipitation. DHT22 informs us of an abrupt increase in humidity. ST045 which gives us the amount of water that fell. RCL5 pieces detects humidity in the ground. The exact position of the phenomenon's trigger will be sent directly to the technical services of the local authorities. In a normal situation, the electronic sentinel stores the measurements taken during 30 minutes in its hard disk and sends them in a single burst. But in an emergency situation, it automatically sends all the measurements every 10 seconds to see the evolution of the situation in real time. We also implement false alarms, forest fire, and flooding. We realize three variants of our simulation. Our simulation involves three scenarios. As the performance criterion, we use the throughput received by the remote server. Calibration values of the detection of the two weather phenomena by each sensor are shown in Table 2. If our electronic sentinel detects these calibration values or values that exceed them, it declares a forest fire or flood emergency dependent on the context and sends the exact GPS position directly to the remote server. In Figure 14, we observe that the throughput received by the remote server is higher when it is the third scenario, whereas for the second and first scenario, we notice peaks of relatively low throughput efficiency centered only around the periods when the periodic reports ascend. In Figure 15, we notice almost identical evolution to the previous figure, with a slight decrease in throughput for the three scenarios. As for Figure 16, we observe almost identical evolutions to the previous figures for the first and second scenario, while in the third scenario we notice a very low throughput and over short periods of time. According to the results, we can clearly see the impact of our intelligent system for the detection and monitoring of meteorological phenomena on the proper functioning of our electronic sentinel. This intelligent system is based on two different phases: training and test phase. The first phase allows our electronic sentinel to memorize the characteristics of each meteorological phenomenon, while the second phase helps our sentinel to recognize the type of phenomenon and the appropriate behavior to follow based on the characteristics acquired in the training phase. Through this research work, we aspire to develop the upcoming sensor networks that must be free from energy consumption limitations, thus ensuring a significant data processing capacity and increased security of communications in the context of a network, which leads us to bring together all these aspects during design and prototyping of our electronic sentinel, made up of several modules including a multitude of sensors. Our electronic sentinel is able to automatically detect and monitor various meteorological phenomena in real time. Indeed, based on the concepts of learning machine, machine learning or electronic sentinel learns about each meteorological phenomenon and stores its characteristics in the knowledge base. Finally, through this study, we propose perspectives for future works to adopt new methods of software engineering for the development of smart applications such as smart environments, smart agriculture, or smart cities, etc. Obviously, the next step will be combining the research field of electronic sentinels with the Internet of Things in order to develop new algorithms for optimal management of data flows. Finally, we suggest building a network of electronic sentinels to contribute to the sustainable development of large geographical areas, city, region, country, etc. And that brings us to the end. Thank you so much for your interest and attention. If anyone has any questions, I'd be happy to open up the discussion. If you would like more information, here is the list of some useful references.